One talk is by Roberto Emparan from the University of Barcelona. He will tell us about the large D limit of general relativity. So please.
Thank you. Thank you for the invitation. So this talk is about a program that we're developing. That's in collaboration with a number of people. Kentaro Tanabe is a postdoc in our group in Barcelona. Yotaku Suzuki is a graduate student. Well, he's already graduated in Kyoto. And then we also had another paper with Daniel Grumiller from Vienna. So what I'm going to talk about is the Einstein equations, which, of course, as we all know, even in their simplest incarnations, they encode a large amount of physics, of interest not just to astrophysics or cosmology, but as we're seeing in this program, it can also have a description. They can also encode a description of other strongly coupled systems, superconductors, and so on. Right? So that's very nice that we have this simple set of equations with a lot of physics. But then the problem, of course, is that these equations are very hard to solve, and this is something that many of you, probably most of you, know by experience, that it's very difficult to find solutions unless you have a large amount of symmetry in the problem. Right. So what do we do in these situations in physics? What is what we do? Well, here's a statement about a similar situation by a famous person. That one has to resort to the indignity of numerical situations to solve problems. Of course, I mean, don't get me wrong. I'm not saying that numerical simulations, there's indignity in working in that. Numerical relativity, in fact, it's a very honorable subject. Right? And I mean it. Right? And it's a very mature, and it's an incredibly useful tool. It's well developed by now. But as we all know as well, when you have a numerical solution, very often it's difficult to extract insights from it. And this is also something that we're seeing in this workshop, that there are some numerical results. You find some intriguing numbers, and you would like to understand where they come from. And for this, we usually it's usually much better to have some analytical tool to solve and understand equations. Okay. So what is then the strategy? Well, strategy in physics is usually to try to find a small parameter that allows you to simplify the theory. And we know, well, there's an old example and very successful example of quantum electrodynamics around the limit of where the theory becomes free. And another limit which is also very useful, it's a little less obvious, but it was realized some almost 40 years ago that it's a very good limit, and in fact this limit is one of the reasons that we're here, that in Yang-Mills theories, and the limit where the number of colors becomes very large, so 1 over n is a small parameter, then this simplifies the theory a lot. Right? So then can we do something similar with the Einstein equations, and in particular with this extremely simple set of equations, where do we find a parameter? Right? It's not visible, the equations don't seem to contain any parameter, but the point of my talk is that the natural parameter for these equations, and in fact the natural parameter for general relativity in general, is the number of dimensions. So if we change it, and if we take d to be large, then we're going to have a small number, 1 over d, that we can use to our benefit. So why do we want to do it? What can we expect to get from this large d expansion? Well, there are two things that I think we can learn from it, from this large d expansion. One of them is that maybe we can get a better understanding of the theory, just like the large n limit of Yang-Mills theories leads you to reformulate the theory in terms of a different set of variables, wall-seed variables, and that's a very useful approach. It's something that's not obvious if you work at finite d in a perturbative way, that you're going to have a reformulation in these variables, but that's something that happens. So maybe we can expect to find another reformulation of general relativity around the limit of infinite number of dimensions in a different set of variables. This is something that we still don't know whether it works or how it could work, but we have some hints. And then, of course, there's the practical application, which is that once we have a small parameter, then we can perform perturbative calculations. Okay. And in this talk, I will focus mostly on this aspect. I will mention a few.
We are watching this with great interest because, in the context of holography, right, when you go to the binding field theory, condensed matter, there's a whole tradition on using 1 over d as a small parameter for strongly coupled theory. DMFT.
So that's
what happened.
I think, taking D as a parameter, that's something that in other fields, also when I talk to people who work in statistical physics, for them it's many of the results that I will discuss here, they are kind of familiar to them, but I think that they were less familiar in the context of general relativity. In fact, I found when first discussing large D, there were some people who showed some resistance to considering an infinite number of dimensions. Maybe, of course, we're used to having a large number of dimensions, 11 or 10 or 26, but going all the way to infinity seemed like a bit of a stretch. Of course, I'm not saying that I believe that the universe could have an infinite number of dimensions. This is something that we use as a tool to understand the theory. Okay, so let me first get something out of the way, which is when one approaches this subject, there's a temptation to take this analogy with the Lachen limit of Young-Mills theories to take it maybe a little too seriously. In fact, it's something that at first sight it could look like a good idea to study the Feynman diagrams of the theory, just like you do in Young-Mills theories, and then try to organize the perturbative expansion in terms of Feynman diagrams by the powers of n or of d that you get. And the analogy might look at first sight like something might work, because, well, in general relativity, the gauge group, the rank of the gauge group, grows with d in a way that's very similar to the way that it grows in SUN gauge theories. So what we have, so in gauge theories, what we have is a large number of colors. Here, what we have is a large number, which grows like d squared, of graviton polarizations. So maybe these diagrams arrange themselves in a similar way to the way that they arrange themselves in Young-Mills theories. Okay, the problem is that this doesn't seem to work very well, because in quantum general relativity, when you study these diagrams, you find that the limit is not dominated by planar diagrams. So this seems to preclude the possibility that the limit is dominated by some kind of worldsheet theory. But further problem, probably a more serious problem, is that you have that D enters not only in the number of graviton polarizations, but also when you want to perform any momentum or space integrals, if you want to compute the Feynman intervals for a diagram, then you find that there are the UV divergences just get infinitely bad. So that's a serious problem, and I don't think that anybody has found a way to get around it. So I mentioned this just because it's a natural idea, but I don't think this is the right way to approach the large D limit of general relativity, quantum theory. So the large D limit of the quantum theory may not be well defined, but the large D limit of the classical theory is well defined. The Einstein equations are well defined at any D, right? And maybe it's a good idea to begin with a classical limit. Yes?
Why can't you take it off in the other dimensions, since in the end you only want to have Lorentz invariance for...
Yeah, so you mean that I'm not so a cutoff in the something that one could do is a Kaluza-Klein truncation of the spectrum. So you get a four-dimensional ultraviolet behavior, and you keep the graviton polarizations in the extra dimensions. That's something that you could do. So in this way, the ultraviolet behavior would be that of a four-dimensional gravitational theory, which is not very good. So that, then, well, what you get from the large number of graviton polarizations is something that, again, it's not dominated, doesn't seem to be dominated by planar diagrams. So it's not clear that this limit is any useful. I mean, maybe one can do something, but I haven't seen any practical application coming out of it. Okay. But on the other hand, as I was saying, maybe it's better to start, well, to try to understand first the classical theory before going on to the quantum theory. Because after all, we all know that a lot of the main properties, a lot of what we know about quantum gravity has been learned from the physics, semi-classical physics of black holes. And black holes are very good at hiding bad ultraviolet behavior. So maybe, before going on to the quantum theory, I think it's a good idea to try to understand the classical one. Okay? Now let me also say that some of the similar motivational techniques, as I will discuss in this talk, were developed by Barak Cole, but yeah, his group. But he only applied it for a very particular case, which was the large D study of the zero mode, the Euclidean zero mode of the Schwarzschild solution. Maybe you can take it any further. So now we're trying to build this into a more complete program. So if we're not going to study the Feynman diagrams, if we're not going to study quantum correlation functions like one does in Yang-Mills theories, then where do we start? How do we take the large D limit? Deciding how do you take the large D limit is, in some sense, it requires you to have an idea of what you think the theory is, right? You may want to take the limit if you take the Einstein equations and R mu nu equals 0 and take D to infinity, well, you don't see anything. Maybe you want to formulate the theory in a different way. Maybe you can try to write the equations in the ADM formalism and take the large limit there. This is something that I haven't managed to get anything interesting out of it. So what we're going to do here is to try to take a different point of view. So what's the theory of general relativity, in particular the theory in vacuum? Well, I think that the theory of general relativity in vacuum is essentially a theory of black holes that interact with gravitational waves. They exchange them, they emit them, and so on. But the central object here is the black hole. So what I'm going to do in this talk is, in order to take the large D limit, I'm going to focus on the properties of black holes. Okay? And well, the simplest solution, the simplest black hole solution, is the Tangerlini generalization of the Schwarzschild solution to higher dimensions. It's a very simple one. You just replace 1 over R by 1 over R to a different power, dimension-dependent power. And here the solution, well, it comes with a scale, which I call R naught. You could set it to 1, the classical theory, without no problem, but I won't do it. And you would think that, well, this length scale, this is the only scale that you have in the problem, and this sets the scale for every quantity and all the physics that happens in the presence of this solution. Okay? So this is the conventional wisdom, that you only have one scale. But the thing here is that when you consider D as a parameter, and in particular as a parameter that can be large, R naught is not the only scale that you have. You have a dimensionless parameter, and this allows you to construct different scales. Okay? And in particular, since we have this small scale, we will see that in vacuum general relativity, this solution at large D, there appear two different scales which are parametrically separated. One of them is this R naught, the horizon radius, and the other one is this R naught over D, which we will see where it comes from and what its meaning is. I think that this equation, or this inequality, it's not an equation, this inequality, I think it's the main property, the main feature of general relativity in the large D limit. And this talk is essentially a talk about where this inequality comes from, what it means, and how we can put it to use. So what we will see, and this is just a preview of things that I will repeat later in the talk, is that the physics of general relativity, the presence of a black hole, decompose or split into two different sectors, two different regimes. One of them is what we call the far region or far zone dynamics, which occurs at scales which are parametrically in D of the same order as the radius of the black hole. So these are distances which are of this order away from the horizon, and we will see that in this regime the geometry of the space-time is flat and the dynamics is essentially trivial. But then there's also dynamics at a much shorter scale, a short scale away from the horizon, where the dynamics is non-trivial, and we will see this bears some resemblance to string dynamics. Okay. So how do we see the appearance of this short scale, short distance scale? Well, it's very easy to see it. It's something that one can already see from the form of the Newtonian potential in D dimensions. So this is the Newtonian potential, characterized in terms of this radius R naught, which sets the location of the horizon. So as D grows, this potential becomes, well, in this region, flatter and flatter, and here steeper and steeper. Okay? And if you compute what's the gradient of the potential at the horizon, then you get this value. And this value, this is already giving you this different scale that we have in the problem. Okay? So at finite D, it would be set by the same scale as the horizon radius, but when we consider d as a parameter that varies and which can be large, then this number can be much larger, which means that we have a scale which is much smaller than R0 in the problem. We have this separation of scales. This is essentially the origin of this separation of scales.
Yeah, just trying to put it in the GR. So that refers to the tidal forces that you fall the hole and
so curvature.
all except that those otherwise you really get apart by the tidal.
That's right. So this is, so we will see this a little later. So this is also the curvature, the scale for the curvature, and also for the tidal forces. And you can see this from the surface gravity, or from the Riemann curvature, or from Wien tensor. So what we see is that the gravitational potential, you only feel it if you're sufficiently close to the horizon. Otherwise, it's flat. The region where you feel it is the region where this is of order 1, and you can very easily see that this happens when you're at distances of this order. Okay? So there's a very thin sliver around the horizon where the gravitational potential is non-trivial. And this sliver becomes thinner and thinner as d goes to infinity if you keep R not fixed. Okay? So what is the picture that we find in this far zone? Well, say that we're at distances. Our distances are of order R0, and when I say R0, I mean parametrically in d. So my distance could be 100 times R0 as long as d is much larger than 100. Okay? So if we are at distances of this order and we're outside the horizon, at any value of r outside the horizon, then as d goes to infinity, this metric function, which controls the distortion and the curvature of the geometry, this goes to 1, this limit. So essentially what you find is that the geometry outside the black hole on these scales is that of flat space. So the field trivializes completely. There's no gravitational field outside the black hole. So what is the picture that we find then in this fast zone? Well, what we have is that the black hole just becomes a hole cut out in Minkowski space. Okay. It's a hole because, well, the potential becomes infinitely steep at R0, and then it becomes 0 outside it. So this is an impassable barrier for probes of that work around this scale. And you can have as many black holes as you want in this infinite D limit, because they don't interact with each other. This, by the way, you're thinking what happens when you have black holes other than the Schwarzschild black hole. It's again the same. You find holes in space. Okay? So this is, for instance, an exact solution for general relativity in the limit of where d goes to infinity. And I could put as many black holes as I want, as long as their distance is larger than 1 over d. Okay. Now, this is something that we've done, and I'll discuss a little bit later. If you consider things like scattering of waves in the presence of these black holes, then you find that these waves, they are perfectly reflected by the black hole. Okay. So it's a perfect mirror in the limit where d goes to infinity for frequencies or wavelengths of this order. And we have confirmed that this picture, that interaction trivializes, we have confirmed it in a number of examples. For instance, collisions, where if two black holes, if you launch this black hole in this direction, and unless you aim it exactly to the other black hole, then it just passes by without noticing the presence of the other black hole. That's something that we have checked with explicit examples. Also, if you consider binaries, well, binary orbits are not stable, but you can still consider them. You see that there are the radius of the orbits just goes to infinity, and they don't emit any radiation. So two black holes moving in the presence of each other, they just don't emit any radiation. There's no the scattering is completely trivial.
Confused about the reflection. Is it that they miss the black hole? I mean, the fact that at finite d you have absorption cannot be lost at infinity.
You don't have any absorption, so that's I mean we have computed the absorption probability, it goes to 0. That's what I mean.
I'm just puzzled about the perfect reflection. I would say they just miss it. Just to clarify, if you have a black hole
Yeah.
and you're considering an L equals 2 gravitational wave
Yeah.
impinging radially on the black hole, is the statement that that absorption probability goes to 0?
So that absorption, if the frequency or if the wavelength is of this order, that absorption goes to 0.
If the frequency is of that order.
Yeah. If the frequency is grows with d, so if it were of the order of d over r naught, then in that case the absorption goes to 1. The absorption probability goes to 1. That's something that I'll discuss later. But on this scale, which is what characterizes the far zone that we probe in these scales, the absorption probability goes to 0. Of course, if it's an S wave, if it were a scalar S wave, that's different, because in that case you can probe a shorter distance.
And when you said emission, you were talking about binaries?
Yeah, so that's of course a binary, so that depends on how you do things. You could try to, well, consider forcing a black hole to circle around another black hole, because otherwise, I mean, Keplerian orbits, the radius grows larger and larger. But if you say that you force it to move at a finite radius, then the emission of radiation goes to 0 as well.
And now, of course, you say you're forcing it to go at a finite radius with a frequency which is order R naught to the D naught. Is
If the frequency is again on this scale, yeah. If the frequency is much higher, then yeah, you get. So as long as all your probes are on this scale, the dynamics is trivial.
If they collision will be touch each other, will be created some oscillation modes.
So if they touch each other, then they are probing distance scales which are shorter than this one, and then the dynamics is non-trivial. And then
You're essentially confining the potential.
you can say so. It's yeah, it's not exponential in the radius, but.
And Roberto, what's the intuition that explains why in this forced binary case the radiation goes to 0?
Well, you can see that in all these cases, what controls the emission of a radiation is a scale which is so all this is controlled. You always get phase space factor in the emission that goes like omega over omega to d. You make this dimensionless by introducing the appropriate length scale in the problem, which in this case is r naught over d. Now, if you have omega less than d, r naught, if d goes to infinity, this goes to 0. This is a factor that you find in all, when you're computing any process where you're emitting radiation and then you try to find, when you integrate to find what's the total emission rate, then you get from phase space or from momentum space factors, you get power omega to the d minus what, some number.
R naught over D in there, R naught over D in that formula just comes from the quadrupole formula somehow, or?
Let me see. That depends. Yeah, I guess that you could say that it comes from the quadrupole formula. It comes from the gradient of the potential, essentially. But I'm not sure I can give you right now. I could check the calculation again to give you a better reply. But essentially, what you always find is well, some omega times some length, and this length. Let me see. Where do we find it? I think it's that you always get something like surface gravity or some gradient of the potential entering in this. It's the relevant quantity that enters these calculations.
What happens to the S-wave absorption, the horizon area, and all this?
So S-wave absorption, so S-wave, that's something that, well, maybe I'll discuss this a little bit later, because I'm going to discuss in more detail, so maybe we can answer that later.
Just one more time. I'm trying to understand whether this is something which is related to the black holes, or if I added matter to this theory and I had, a long bar of the same total mass, which I forced to spin at this rate, would it also have suppressed radiation?
Yeah. So in that case, so if you add anything to this system, then this is also going to come with some scale, right? So if you add some matter, then this is going to create some field with some gravitational radius.
Yeah.
If you keep the gravitational radius finite as you send d to infinity, which is different than, say, keeping the mass finite as d goes to infinity. But if you keep the gravitational radius finite, then these effects will remain. If you keep the mass finite, then things are going to be different.
Change the distribution of the matter to make it
Yeah,
R instead of
that's
two
right.
things. It will change. It could change the answer.
So you have to adjust. So when you take, this is something that happens always. Whenever you want to take the limit d goes to infinity, you have to decide how the different quantities in your system are going to scale as you take d to infinity. That's like, you also do that, say, in latch and gauge theories. If you have flavors, you have to decide how the number of flavors are going to scale. If you add anything that you add to the system, you have to see how you are going to, depending on how you do the scaling, you're going to get different physics, but that depends on which question you're interested in asking. Okay? But if, as I say, if you keep the length, the radius associated to the gravitational radius of of the field that creates the mass, if you keep it finite, then this is still true.
Are you getting into the black hole entropy?
I'll discuss a little bit later. Okay, so we have this far zone on these scales. Now we focus on the near zone. We go close to the horizon, and we want to keep the gravitational field non-trivial. Okay, so this means that we're going to be on the length scales which are of this order away from the horizon, and this way we keep things like surface gravity or curvature. We keep them finite. In order to take this limit, it's useful to define a new coordinate. This is what we want to keep of order 1. This is what because we want to keep the gravitational potential finite. So we introduce this quantity, and we want to take the limit in such a way that this big R remains finite. So when we do this change of coordinates in the Schwarzschild solution. We take the large D limit. The geometry that we get is of this form. Okay. So you see that this is a small factor. This reflects the fact that well, you cross the region. This region in a small time. One thing that you can do with this geometry, because this the form of this geometry may not be quite familiar to you, but if you change to a more appropriate time coordinate that measures the time that it takes you to cross this near horizon region, and then you also perform a change of coordinates in the radial variable, then the geometry that you find here is that of a well-known solution. It's the black hole, the two-dimensional black hole of string theory, which was found in the early 90s by Witten and a number of other people. Okay? So this is something that is fairly surprising, maybe, that you find something that looks stringy in this large D limit of general relativity. You find this geometry. And one thing that we can do is identify what we would call, say, what you would call the string length in this system, which is of this order. So the small scale in general relativity, this scale R naught over D, that's what we might call the string scale. Okay. So we have this near zone, and the way that we define it, yes?
The scalars of curvature are finite or infinite at the horizon?
So they are 0. So the curvature invariants are 0 outside the horizon. Here they are finite on this scale because we're keeping, so they are of this order.
Okay.
So the scale that controls curvature is this string scale. So if you keep this finite, then they are finite, which is, so in this region, the near zone, we're probing these scales, we're keeping this finite. Okay. So in terms of R naught, in terms of longer, so probes of longer wavelength will fill this as infinite curvature at the horizon, but probes of much shorter wavelength will fill them as finite curvatures. So the near zone, well, it contains not only this region that we call the sphere of influence, but also it extends further. What's good is that, so we have this far region, which excludes the blue region here is where the interaction is non-trivial. So in the far region, interaction is trivial. We have this near region that includes this sphere of influence, but it also extends somewhat further. So we have an overlap between the far and near regions, which is good because we have this separation of scales, but we have an overlap where they match. So this is something that in terms of solving equations is useful because you can perform much asymptotic expansions. You can solve equations in this region, you can solve the equations also in this near region, and then match them to obtain a complete solution. Yes?
So if I understood correctly your answer, then this black hole solution that you have in the near zone, it's not a solution to the full equations of motion, right? It's like in this near horizons limit that you take some time.
No, it's,
is it still a solution of R mu nu equals 0? I think.
Yeah, it's a solution to R mu equals 0 to the leading order in 1 over D. It is.
Okay.
Well, this you also have to do, and this sphere has a large radius. If you focus on shorter scales on the horizon, then this is something that scales into this 2D black hole times a plane if you blow this up. But that's a solution.
But it's only
It's a solution to R mu equals 0 to leading order in 1 over D.
If you compute the Riemann, the Ricci curvature, you will find it's proportional to 1 over D.
If I compute what
The Ricci curvature.
the Ricci tensor, yeah, so that's 0 to 1 over D.
like, sometimes.
I mean, it's 1 over D solution.
But there are terms which are for the 1 over D.
Yeah, so there are corrections.
Yeah.
Because presumably these people, when they found that black hole, they were not looking at R mu equals 0, right? They were
So
looking
the way that this is found is that you begin with a solution that satisfies R mu equals 0, and then you expand it.
I understand perfectly how you got it, but I mean, in these original papers, presumably.
Oh, no. These guys were solving the equations, just the 2D part. So that's something that you do here, and I'm not explaining it. Well, I could explain, I could discuss it. So let me see. Okay, so here it is. So the way that you get this, you restrict, you truncate to S waves, to the S wave sector, spherical symmetry sector. You have a two-dimensional theory, there's a dilaton. In general, this is what you get. So solutions of this, it's not R mu in 2 dimensions, and R mu equals 0 is not 0 in 2 dimensions, but this is the two-dimensional R mu. So you have a dilaton gravity, so you have the dilaton, you have the graviton, you have these dependent factors. When you take V to infinity, then this becomes this action, the effective action of a string theory in 2 dimensions. Okay. So that's so what I'm doing is I'm truncating the infinite number of degrees of freedom that I have in infinite dimensional general relativity. I truncate it to the TR sector, a 2-dimensional sector, and then all of the degrees of freedom in the sphere, I just freeze them and I just consider the radial mode. In fact, this theory doesn't have any degrees of freedom, just because the spherically symmetric sector of general relativity doesn't have any degrees of freedom. Okay. So it's a solution to this, what Witten and the others solved were the equations of this theory. Okay. What we're saying is that the equations of this theory are the largely limit of the equations of the Fuller theory, of the Fuller infinite dimensional theory to leading order.
It's morally similar to Weissman-Nordstrom black hole, where
Yeah.
it's in the radial time plane and the spatial dimensions are just fetching.
That's yeah. So it's
If you added non-spherical terms to that action perturbatively,
Yes.
what would that look like?
So if you consider, say, perturbations of this,
Add non-spherical terms.
so if I add, say, or if I introduce a perturbation and then I decompose it, say, in spherical harmonics, then what this gives me is that each spherical harmonic gives me a scalar, a massive scalar in this theory. It's not a minimally coupled scalar, but it's a non-minimally coupled massive scalar. So in general, perturbations of this geometry will give me an infinite number of massive two-dimensional scalars non-minimally coupled. Non-minimally coupled in 2 dimensions.
How axions appear? Two-dimensional axions. What is action?
An axion.
The axion.
So the axion can come if you consider not Einstein-Hilbert, but you consider some action in higher dimensions. That's something that I will discuss an example later. Oops. What was I? Okay, so I think as I was saying, so we have this overlap between the near and far zones, which we can use in order to perform much asymptotic expansion solutions of the equations in this geometry. So, so this is the picture, and it's a picture that's very generic. So we have analyzed not just the Schwarzschild solution, but we have analyzed all available solutions in the market in higher dimensions, and we have seen that the pattern is general, that the far region, the region outside the horizon, is just flat space or empty space with holes that do not interact with each other. And this is something that we've checked for charged black holes, for rotating black holes, for the black holes in anti-de Sitter. In anti-de Sitter, instead of being flat space, what you find is empty anti-de Sitter space outside the holes. For extremal black holes, it also holds, and so on. And in fact, the picture is, I think it's quite general. It just follows from the fact that if you have a black hole, if the surface gravity is uniform, then that's the place where you have this abrupt jump away from the horizon. Yes?
What happens to the superradiance effect as you go into infinity, like in the rotating cases?
Yeah. Maybe we can discuss this later. That's would take me. I mean, that's. I'm just discussing now the basic solutions. Then dynamics around them. That's something that I will discuss later. Maybe you can ask the question later, or maybe we can discuss it in private. Okay. I'm not sure I can give you a short, clear answer right now. I have an answer because we've thought about it, but it will take me a while. Okay, so this is the far region. It's essentially this picture. For the near region, in this case, well, you retain the dynamics, so things are not going to be so universal. So depending on whether your black hole is charged or not, or extremal or not. For instance, the presence of the extremal throat, that's something that remains if you go to the near horizon region. But what we have found is that the near horizon region, you find this two-dimensional string black hole. It's not just a property of the Schwarzschild solution, it's a property of all neutral non-extremal solutions. So if you take, say, these Myers-Berry solutions, and then you take this large D limit, or you take black holes in ADS and you take the large D limit as well, you always find that the near horizon region is described by this two-dimensional string theory black hole. Okay? If you have charges, then things change. And for instance, if you have a three form, like you were asking before, in this case, we find also some other geometries which are not the two-dimensional string black hole, but some of them also have a stringy interpretation. For instance, if we take the large D limit of non-dilatonic black string with string charge, if we take the large D limit of this solution, what we find is another solution that's well known in string theory because it also has an exact conformal field theory description, and that's a black string in 3 dimensions that Horn and Horowitz found. In other cases, we don't have a string theory interpretation of the large D limit, but we don't really know in which cases one should expect that or not. But this is again one more hint that some string theory might be lurking behind on this limit. Now let me mention, since this is a workshop where anti-de Sitter space is prominent, let me say a few things about how you take the large D limit for black holes in anti-de Sitter. Well, as I was saying, if you have another scale in the problem, then you have to decide how you take the large D limit. What are you going to keep fixed as you take the large D limit? Are you going to keep the cosmological constant fixed? No, that's not a good idea, because that would make the cosmological radius go to 0. So if you want to keep the geometric effects of the cosmological constant, what you have to keep is the cosmological radius finite, which is different than lambda because you have these d factors over here. So we take the limit in such a way that we keep the cosmological radius finite. This keeps a finite geometry with finite ADS effects, and then we take d goes to infinity. Well, this just so happens that this sends the cosmological constant defined in the conventional way. It goes to infinity, to minus infinity. But the gravitational effects remain finite. Now, if we take not just the limit for anti-de Sitter space, but we put a black hole in it, as I said, the picture is essentially the same. We have the same two zones, the far zone, where you have empty space, and then you have a hole cut out in empty space, where you have the black hole. The geometry of this black hole is the geometry of the two-dimensional string theory black hole times this sphere. But let me mention something that might seem puzzling at first, which is that I'm going to consider the black brain because that's so what may be of most interest in holography, or at least to many of you guys.
There's no difference between small and big black holes.
There are you can have small and big black holes. There's a difference. So that difference remains as you take the large
You
limit.
say that applies only to small black holes.
No, what I said applies both to small and large black holes. If you keep their horizon radius finite and you keep L finite, then you still have large and small black holes, and the limit that I described applies to both of them. So you have a small hole which is smaller than the ADS radius, or you have a large hole which is larger than the ADS radius. That's what small and large black holes go to. And then we can take the limit where the black hole becomes very large compared to the ADS radius, and this gives you a black brain. So what we find here is that here we have the boundary, we have empty anti-de space, and then we have a hole cut out in this anti-de space in concrete coordinates, which is a perfectly reflecting hole. Now, you might worry that if you have the black hole here and this is empty space, well, maybe here you don't seem to sense the presence of the black hole. There's no distortion of the geometry. So does this mean that the boundary CFT misses the presence of this black hole down here? Well, things are, well, the boundary, the answer is no, that the boundary CFT doesn't miss the presence of the black hole, but it's a little subtle how it does. The answer is no. So the effect that I described is that if we keep R not finite, then the effects in the metric, they vanish exponentially in D. You have an 1 over R to the D that kills the potential. But then you take the solution, at finite D, you compute what's the energy density, and then you take D to be large. What you find is that the energy density grows like D as the number of dimensions goes to infinity. Also, the temperature grows like D. The thermal circle becomes smaller and smaller. The thing is that for the conformal field theory, the relevant quantity to compute, what you want to keep in the conformal field theory finite, is the temperature. That's what gives you the scale. And if you measure the energy density in units of temperature, then the energy density in these units remains finite. So in a sense, since this quantity is what corresponds to the string scale, the small scale, the CFT sees the two-dimensional string geometry. The limit between these two quantities gives you 1 over 4g, and that's of course something that you already recognize, saying that the entropy density remains finite. Now this property that you have, when you have a spectrum where the entropy density and the energy density are proportional like this is a Hagedorn spectrum. Right? It's a Hagedorn spectrum with a temperature. For a Hagedorn spectrum, you can identify a string temperature. The string temperature would be the temperature of the black hole. In fact, this happens not only just for the ADS black brain, it happens for all neutral black holes in this limit. Another funny property of this limit is that the pressure, and this is something that happens just because of conformal invariance. The relation between pressure and energy density is like this, so when D goes to infinity, if you keep the energy density finite, then the pressure goes to 0. In a sense, the pressure dilutes in all this in these infinite dimensions, right? But what this means is that the system becomes fluffier. It's more and more fluffy. The sound speed vanishes, so the system doesn't react to variations in the pressure. So it's a bit like you have dust, but maybe it's not dust. Maybe it's something different. Maybe the black hole, when D goes to infinity, the black hole behaves more like a gas of strings, a Hagedorn gas of strings, which also has these properties, right? This is something that we don't know. When I say a Hagedorn gas of strings, I don't know what these strings are, where they live, where the target spacetime is, or what, right? So
You're saying it's the same thermodynamics, the same pressure-density relation.
to lead in order, yes. Yes.
Yeah, just ignorant. Is entropy still holographic? I mean, how does the entropy scale with the
So the entropy, this is an entropy that I measure from the area. So, but because this I define to be the Bekenstein-Hawking entropy. Yeah. So I'm not saying, I'm not computing it from any microscopic model, but I mean, if it's CFT, yeah. But as I say, this also happens, this proportionality between the entropy and the energy, the mass, also happens for the Schwarzschild black hole, if you take the limit where D goes to infinity.
Did I understand from your previous slide that if I think about the gauge theory on a fixed size S d cross r, where I fix the radius of the SD, that
The sphere. So I'm here doing it for the black brane.
move the black brane. That's
Yeah.
right. Yes. Okay.
For the SD,
Let's do it.
Yeah.
But you mentioned that in some sense that the temperature of the black hole goes to infinity.
yeah.
So if I was doing, say, Shirk-Swartz with an S1, does that mean that the deconfinement temperature goes to infinity? If I-
So the circle, the compact circle goes to 0, so the associated scale goes to infinity, right? Is it,
compact circle.
let me see, yeah, so the compact circle goes to, yeah, so the length of the circle goes to 0.
Why does it go to 0?
Well, because the temperature, that's the inverse of the, so what I'm saying is that...
Oh, the thermal circle goes to yeah. Right.
This.
Yeah.
So,
So if I chose to consider a Shirk-Swartz compactification where I fix the size of the extra circle with the deconfinement temperature go to infinity.
yeah.
And are any of these results known for large D gauge theory? Since you mentioned that there's a history of...
I don't know. There's some work on the large-D limit of. I mean, there's work on generic properties of conformal field theories in arbitrary D, which people here in the audience have studied. In those cases, I don't think that the large-D limit was considered, but this year there was a paper on. Some people analyzed the large-D limit of conformal blocks. I don't think that it's been taken further than this, the large-D limit analysis. Of course, we don't know whether conformal field theories exist.
I think it's a simple matter of order of limits, right? So in statistical physics and so forth, you don't have to do conformal field theory, it's completely important. Large D is the way to get Gaussian fixed points.
I see.
So the question is, when you make a finite tooth coupling and a finite
Yeah.
and you send matters to infinite dimensions, I expect a free theory.
Yeah, here the limit that I'm taking is different, right?
Yeah, I think so.
Taking first infinite D, and then
Note that when you look at the entropy, that there is a prefactor, it's always 2 to the power D.
yeah.
By a prefactor, that's somewhat different for the large tooth coupling CU and for the free CU. Can you read of its prefactor and conclude that it's still behaving?
I don't know. We haven't done. I mean, this is very preliminary. This is something. Studying this in more detail, it's on our to-do list. So we haven't got much further. But so what you're saying is first taking infinite D and then keep finite N.
And the tooth coupling finite, so
Yeah.
to infinite, you will have a constant CU. The other way around, you will have.
Yeah, I don't know if we can do that because the way that we're doing it is the opposite. Because we're going to the classical limit to large.
Check whether it's really true that.
But it would be interesting to see whether. Yeah.
Well, you don't have to worry about tooth coupling because gauge theories are going to be weakly coupled in an infrared large D. So you don't even expect that
Well, that's exactly
you
the
have a
issue,
holographic dual of a gauge theory.
Yeah.
But of course there are free field
But the
theories
gauge theory,
which
right? When you
conform-
start out, Andre, this is the issue. When you start out with infinite coupling in the gauge theory, you send D to infinite, right? In that limiting procedure, you'll start continue to see the Sony integrated theory, right? And then when you do the other way around, you get a free theory.
Well, generally you don't
It's the
expect
single limit.
holographic duals, gravitational holographic duals of large D gauge theories.
They have to be studied, you were saying.
And of course that's what happens if you consider D branes with D larger than 4. But there are of course free field theories with P forms, which are going to be conformal invariant.
I exactly say, right? So it's a law in statistical physics that for any finite coupling, there is a D to infinite, you have a free theory. That's a law.
Okay.
How do you show this?
Yeah, I would like to know more about this. So that's a law.
Yeah, essentially because epsilon spatial depth, right? That makes a localization, right? And eventually when D is infinite, it kills all the fluctuation.
Okay. Well, maybe I think that's very interesting, but.
Very well known classic.
Okay, maybe we can continue because
Same thing as last year.
So.
For sure it is. What is your upper critical dimension? You know?
Because I want to, well, the time that I have left to describe
Is infinite.
how we've
You always.
applied this large limit to some specific cases. So the cases that I'm going to try to describe, I don't know whether I'll get to all of them, are first of all, well, the simplest thing that you can do is try to study scalar propagation in the presence of a black hole and study things like absorption probability, the scattering problem, or quasi-normal modes. Then another problem which is was useful for us as a benchmark for the accuracy of the method was to study the Blackbody instability. And then something that we're working on, and we have, it's very preliminary, it's a problem of critical collapse. So just, I'm not going to show you the calculations, but the way to set up the calculation is what I said. So in the first zone, we have the scalar field is just propagating in flat space, but then you have to, when you reach the region close to the horizon, then you solve non-trivial equations. Here you're essentially studying the black hole excitations. So you match the solutions, and then this gives you a full solution to the scattering problem. So we have a complete analytic solution to the problem of scattering of a scalar field in the presence of the black hole. We can reduce this to an effective theory. Since we have this separation of scales, what we can do is integrate out the short distance scales. That's integrate the equations in the near zone, imposing regularity of the horizon of the field. And what this gives us is effective boundary conditions for the fields that propagate in the outside region. So what we get out of this analysis, integrating out this near zone, what this gives us is effective boundary conditions determined from the near solution for the propagation of the field in the flat space. So this is an effective theory. So we can view this as a classical effective theory, but it's an efficient way of describing the scattering problem. Now, the result is that we have an analytic calculation. It's a formula that I'm not showing. It's not terribly complicated. It can be written in a line or two. It's fully explicit, but its properties are very easily studied. So if we have, if we're considering scattering at frequencies which are smaller than a critical frequency, and that's set by this scale, this is what we were discussing earlier, this is what we call the string scale, then the absorption goes to 0. So we have a perfect mirror, whereas frequencies which are larger than this scale, the absorption goes to 1. So it's a very drastic change. It's a step function. Now, if we consider, say, S-wave, propagation of S-waves, and we go to the low frequency limit, then we recover a well-known result, that to lead in order, at the low frequencies, the cross-section for S-wave absorption is proportional to the horizon area. Now, our formula gives us, well, a full result, but we can expand it, say, at small frequencies and get this correction. I don't think that this correction had been computed analytically before, corrections to this result. And that's something that comes out very easily. In fact, we have, well, much fuller expression that contains this as a limit. Okay, so that's a problem that we can solve. Propagation in the black hole, we have all the transmission reflection coefficients. The other problem that you can try to analyze is that of quasi-normal modes. This we have analyzed again for the scalar field. Now I have to say that the scalar field propagation in the presence of the black hole, it's isospectral. You get the same equation if you consider also some gravitational perturbations. Gravitational perturbations can be decomposed according to the tensorial character in the sphere. There are scalars, vectors, and tensors. The tensors happen to satisfy exactly the same equation. By the way, the tensors are the most numerous modes at large d. Right? So the equation, you can write them, the equation for these fields, you can write them in the form, this Regge-Wheeler form, which is a form, you get an effective potential, which for the Schwarzschild black hole, as d grows large, takes a shape of this kind. So this is the region near the horizon, this is infinity. Here you have essentially flat space, you get the centrifugal barrier, and the height of this barrier grows with e. This is why the absorption cross-section had this abrupt behavior. If you have frequencies that probe only this region, the absorption probability goes to 0. If they are larger, then they just fly through to the horizon. So this is the potential that we have to study in order to find quasi-normal modes. The problem of quasi-normal modes is that of finding modes that satisfy that they are ingoing towards the horizon and outgoing towards infinity. Now this problem is well known, in this case, that it can be mapped to a problem of finding the quasi-normal, the bound states in the inverted potential. Essentially, you perform an analytical continuation where these plane waves are exponentially damped in the inverted potential. Okay?
Roberto, you're already over time.
I'm already over time. Over. Okay. So, well, what we get when d goes to infinity is that this potential becomes very pointy. In fact, it becomes just a sharp point. So the problem that you have to solve here, the problem is that of solving quantum mechanics in a triangular potential, which is something that you do in your undergraduate courses in quantum mechanics. This gives you 80 wave functions, so we can get the spectrum of quasi-normal modes out of these 80 wave functions. And well, we have full results. Modes, the real part of the modes goes like this, and the imaginary part is much smaller. So these are very short, long-lived excitations. It's a bit like they are quasi-particles. Let me also go briefly over this other problem, the problem of Evreux-Laflamme instability. I think that most of you have seen it before. A black string is unstable to developing these ripples. This is a bit like fluids do. So these perturbations grow exponentially in time, and you have a spectrum of perturbations. So the imaginary frequency depends on wave number. This is something that Gregory and Laflamme they computed this dispersion relation by perturbing the black string and solving the equations numerically, and they found a shape like this for the spectrum of unstable modes. Okay, so what we've done is to solve this problem in the large D limit, the large D expansion. So we've done this calculation of solving the far region, the near region, back and forth, this game of going back and forth order by order, and we've performed it up to fourth order. The result is this. This is as far as we could get analytically in terms of these variables, and this is an expression. A particular case of this had been worked out by Cole. So we can now try to compare this analytical result with numerical results that are available in different number of dimensions. So the numerical results, so Pau gave us results from his numerical codes for this problem, and you see that the large D expansion is extremely good. So n here is D minus 4, because n equals 1 is the first case where you have non-trivial black strings, that's in 5 dimensions. So you see that already for n equals 3, you get an excellent match to the numerical results. And for any n larger than 3, the accuracy of our results is very good. So I think that this is very encouraging. It's not that we were so interested in understanding this. So we were using this problem, the problem of black brain instability, as a benchmark to see how good these methods could be. And we see that they can be very good. Okay. Now, last thing that I want to mention a little bit, and this is very much in progress, so you should take everything that I say here with some grains of salt. So you know critical collapse. This is the problem that if you have, say, massless field, massless scalar field in a spherical symmetric configuration collapsing, you send it inwards, and you consider a one-parameter family of initial conditions, say you can vary the amplitude of the wave or some other parameter. Well, there's a range in which the field collapses and form a black hole. There's another range for some other values of the parameter where the field disperses away, and there's a critical solution, which is singular, which you can characterize in terms of a critical exponent. This solution also exhibits a phenomenon that's known as discrete self-similarity. It's kind of an echoing near the critical region. So what happens in the large D limit? Well, in the large D limit, this problem of collapse is dominated by this short distance region, where we have this effective string theory action. Right? So we have the problem is essentially described by the effective two-dimensional string theory plus the scalar field that you have, which in 2 dimensions is not a minimally coupled scalar. The situation this is somewhat similar to what happens in the CGHS model of 2-dimensional black holes. It's different because in this case, well, this model also incorporated quantum effects, but it also there was also the fact that the scalar that appears in the scalars that people study, including this model, are minimally coupled in 2 dimensions. Now, the critical collapse for this model was studied, I think, by Strominger and Thorlasius. They found a critical exponent which was 1/2, which is also what we were conjecturing should happen also for the large limit of general relativity, of the collapse in general relativity coupled to a scalar. we're making some progress in this problem, but we're still not there. What we have found is that if we consider that if we assume that at d goes to infinity, the discrete self-similarity becomes continuous self-similarity, the echoing period goes to 0, then we can recover this exponent gamma equals 1/2. But then there's the question of 1/d corrections. Okay, that would be interesting. So this is under some assumptions that maybe at some point we'll have to drop. But so far, we're assuming that we don't know whether this is completely true or not, but we're assuming this so far. So we get this value. For the 1/d corrections, well, we have a conjecture for what could be the result. There are some numerical results available. If you try to perform the simplest fit to these results by adding this 1/d correction, this is what you get. So this is a fairly good fit, and it's amazingly good if you set d equals 4. D equals 4, the numerical value is this one. If you plug this here, then this is, but this is probably an accident, right? This could be 1/d, or it could be 1/d plus 1. At this order, we don't know. 1/d plus 1 gives you a better fit here, but it becomes worse here. The thing is that if we consider 1/d corrections, then this assumption of continuous self-similarity is probably going to break down. We can work out these corrections assuming continuous self-similarity. What we get is a different result. So we have to incorporate this, and this is something that we're working on. So I'll just finish advertising the method as a practical method for solving general relativity, because whenever you can formulate things in arbitrary d, you can take d as a parameter. The way to do it is not that you just go to your equations and take d to infinity. When you try to do that, you realize that, well, you have to decide how other things are going to scale, how other things are going to change. What we have argued is that the way to organize the calculations is to first focus on the regime of far regions, where all your scales are of this order, then solving the near region, where your scales are of this order, and then you get some two-dimensional string black hole with some conformal symmetry that can help you, and then you match. This is the practical way of doing things, and we have argued that this can be done, and it can be very efficient. And then, of course, there's the idea that there might be some string theory lurking behind this construction. But this is something that we don't really know whether that's true or not. And well, with this, I'll stop, and thank you. Thank you for your attention.
We have time for one more question.
Yeah, very quick. From your quasi-normal mode analysis, do I get it right that in the boundary dual, it would mean that at least at low frequencies, indeed infrared, you would have just only sharp poles and nothing else when you look at properties?
Yeah, so well, what I said, that was for the Schwarzschild black hole in that space. We have also done some analysis in the for the ADS, for black brains. So that picture of this point, this doesn't apply to the hydrodynamic modes in the ADS. So the hydrodynamic modes wouldn't show this, I don't think that they would show this quasi-particle property, this Sarkovic. The modes that, so if you have a large black hole in anti-de-Sitter, say it's a large in the global ADS, you consider a large black hole, there are two kinds of quasi-normal modes. Some of them are what some people call slow modes, which are the ones that become hydrodynamic when you take the very large black hole limit, and the other ones are fast modes with frequencies that are proportional to the temperature. These fast modes, this would be more like these quasi-particles. The slow modes, the hydrodynamic modes, they are not. They are different. I'm not sure whether I mean...
Yeah, no, that's fine. It's more like, I mean, for the future, but there's this issue, right? Whether you somehow realize some free field theory.
Yeah.
You have to ask the question, perhaps at zero temperature.
At zero temperature.
Right? Because hydro, of course,
Yeah.
polishes,
Yeah.
whatever, there you cannot do.
I think that should be interesting.
Zero temperature, you have the fast modes, and these are all pure quasi-particles,
Yes.
suggestive that there's a free theory.
Yeah.
Realizing.
Yeah, I agree that that's interesting. That's something that we haven't studied yet, but I think it's an interesting also.
Okay, so let's thanks the speaker again.